Okay, hello, my name is Alex Arsenovic, and I'm going to give a presentation about the applications of conformal geometric algebra to transmission line theory. Alright, so before we start, I'm just going to give a brief summary of the larger project which this is a part of, called geometric network theory. And okay, so to provide some context for this project, the conventional approach to network theory is based on complex numbers. The problem, complex numbers, is that they're not scalable. They only work in two dimensions. So generally, network theory is taught using a series of Möbius transformations over the field of complex numbers, and they can be expressed in this form. The problem with Möbius transformations is that they're nonlinear. So when you compose a set of them, the result gets more complex at every step. So the solution is usually to go to matrix representations of networks. The problem with this is that they're not very interpretable geometrically, and so this kind of hinders theoretical development. Okay, so like I was describing just a second ago, the shortcomings, a major one is that the underlying geometry is hidden. Another large problem is that using these dissimilar systems creates disjointed models, so there's a lot of redundancy, and this results in less robust algorithms. So just to give you an example, so in two dimensions we know that you can rotate vectors with complex numbers, but then in three dimensions we have to start using rotation matrices. So why is that? What's the problem? Why can't we do the same thing in both spaces? Okay, and another problem is that using matrices of complex numbers will complicate the analysis unnecessarily. So here's another example. So we can write the modulus of a complex number squared in this format, but if we were using matrices of real numbers, we'd have to express it in this format, this is much more complicated than this, much less concise. So similarly, geometric algebra is going to let us express complex matrices in a more concise way. And all of these little problems create barriers between expressing the theory and then actually implementing results in algorithms. Okay, so what's our idea? So the idea, like I was just mentioning, is to reformulate network theory of geometric algebra, and I'm going to get to that in a minute, what that is. The goal is that the relationships, quantities, and conditions, they're all going to become geometrically interpretable objects. Okay, and we're going to start with transmission line theory. It's a good place to start because that's usually how network theory is developed, and it's also a very old subject. So here's just a brief graphic showing our evolution, so to speak. We're going to start with the Smith chart, which is a two-dimensional space representing reflection coefficient. Then we're going to add a dimension and move into a stereographic projection model known as the Riemann Sphere. We're going to do this because it's going to give us a little bit of intuition about how to use projective geometry, and it's going to simplify certain operations, but not all of them. And to remedy that problem, we're going to move into a four-dimensional Minkowski space and using a tool known as conformal geometric algebra. Okay, so here's the outline of the talk. So first I'm going to describe complex numbers and projective geometry just to give a little bit of context and background. Then I'm going to give a brief introduction to geometric algebra. Then we're going to move on to the Riemann Sphere. We're going to find some problems with the Riemann Sphere, which is going to motivate us to use conformal geometric algebra. And then we're going to discuss some transmission line theory with this. Finally, we're going to give an example of analyzing a distributed circuit model and move on to a conclusion. There's some other examples in the paper about impedance matching, but they're not given in this presentation just out of time considerations. Okay, so complex numbers and projective geometry. Okay, so we all know that linear time invariant systems only affect the operations of shift and scale on sinusoid. So this graphic just illustrates we have some input sinusoid, which is this blue curve over time. So y-axis is amplitude, x-axis is time. And then the red curve is the output of the system, one possible output, where it's been scaled by alpha and phase shifted by theta. So linear time invariant systems can be analyzed by restricting the transforms at any given frequency to these two specific transforms. Okay, so generally what we're going to do is linearize this. So the problem is that phase shifting is not a linear operation like scaling is, so we need a trick to linearize it. And the trick happens to be that we're going to create a helix in three-dimensional space. So here I have a value on this axis and then some added dimension here, which I'm not really interpreting physically, and then I have time on this axis here. And we're going to see that if you plot a helix here, which you can express as a complex exponential, and you take the orthographic projection onto this plane, then by spinning the helix, you'll see that this projection basically shifts left and right, or forward and backward, if you will, which is expressed by this equation here. And that's the reason we're going to use complex numbers, and that's why they're useful for linear time invariant system analysis. Okay, so just like we are going to use complex numbers to linearize phase shifting, we're going to use conformal geometric algebra to linearize Möbius transformations. Okay, why we're going to do this? Because microwave engineering requires more operations than just shift and scale. Most of the relationships are Möbius transformations, and CGA will linearize these. So that's the argument, and that's the line of thinking, and here's the same graphic illustrating our evolution that we're going to go through in detail. Okay, so what's geometric algebra? So from electrical engineering perspective, it's best thought of as the extension of complex numbers to n dimensions. Okay, so to do this, commutativity has to be abandoned. And this is kind of obvious if you want to use our algebra to model rotations in more than 2 dimensions, because rotations don't commute in 3 dimensions and not in other dimensions either. Okay, so geometric algebra is going to subsume many independent systems like complex numbers, quaternions, vector calculus, matrices, and the list goes on. Okay, so how is it going to do this? It does this by introducing new mathematical objects and operators. So a lot of these operators in 2 and 3 dimensions, electrical engineers are already familiar with through complex numbers and vector calculus. So it's actually really easy, or easier for electrical engineers to adopt geometric algebra than other disciplines, perhaps. But okay, here's an illustration of the different objects that geometric algebra introduces. So we have a scalar here, which is just represented by a point, some value, then a vector. Okay, now we're stuck in this field over these objects normally, so what we're going to do with geometric algebra is extend that, and we're going to create an object called a bivector, which represents an oriented plane segment, and it's expressed this way because 2 vectors define a plane. And similarly, you can keep doing that to generate a trivector out of 3 vectors, and so on and so forth. So we have a larger field of objects over which we can apply operations. Okay, so the key to geometric algebra is the notion of the geometric product. So it's a different kind of product than we're used to using. And it can be introduced in this way. So first we just assume that a vector is going to square to a scalar. And that if you sum 2 vectors, it's going to be a vector. So if we assume A and B are vectors, and we sum them, we know this will be a vector. And if we square it, we know it's going to be a scalar. So, okay, these things, these are squared. The vector magnitude squared. So this thing right here has to be a scalar if we assume that to be true. So this product we're going to call the inner product, and it's defined by this. And we're all familiar with that. Okay, so then we say, okay, well, the product, the symmetric part of the product is useful because we can do things like describe projections and things with it. Why don't we consider a balanced approach to a product where we break it up into a symmetric and an anti-symmetric part? And this is kind of starting to look like complex numbers. But we're going to attribute a geometrical meaning to this anti-symmetric part. We're going to call it a bivector. And we're going to denote this kind of product here with the wedge symbol. And just so you know, by definition, this implies that changing the order of the vectors reverses the sign, which makes sense if you consider it to be an oriented plane segment that's swept out by 2 vectors. Okay, so a geometric product returns 2 different types, a scalar and a bivector. So in geometric algebra, these are called grades. So a vector is grade 1, scalar is grade 0, and a bivector is grade 2, and so forth. Okay, so what we do is we generate, they say, a geometric algebra given a certain basis. So in 2 dimensions, we're going to pick 2 vectors, e sub 1, e sub 2, and then we're going to say that they are normalized here, and they're orthonormal. That's not expressed here, but let's just assume that's true. And then by taking the product of these 2 vectors, we're going to generate a bivector. And this bivector describes the plane which we're talking about. And this thing squares to -1 based on the rules I described above. So this is going to give us, essentially, you can imagine this is a complex number, the complex unit imaginary. This is the real, and this is just a vector space. Okay, so how do we do rotation? So in complex numbers, we rotate things like this. So W is a complex number, and we're going to rotate it using a complex exponential of e to the theta j. Rotate the vector z. So in geometric algebra it's similar, except there's what they call a two-sided or a sandwich product rule, where you put a rotation half angle on either side of it. And the reason you have to do this is because this is the way to generalize rotations to arbitrary dimensions. So we might as well start doing it too. Okay, so this thing right here is called a spinner. If it's normalized, meaning it doesn't have any scaling factor, which this doesn't either, you can also refer to that as a rotor. Okay, so now we're going to map complex numbers into the geometric algebra so we can get to work. So here we have the complex plane, or the Argand plane. A vector z is represented by a real and imaginary component. Okay, so there's 2 planes in the geometric algebra of 2 dimensions. We have a vector plane, and we have what they call a spinner I plane, or a spinner E12 plane. So this represents scalar and the bivector, and then this represents the 2 vectors. So these can be mapped to one another, so you can kind of pick which one you want to associate the complex number with, depending on your application. So what we're going to do is map it from the complex plane to the spinner I plane to the vector. Okay, and just to give you an idea, okay, how does this generalize in 3 dimensions? So it's pretty similar. We have here an orthogonal 3-dimensional coordinate system, E1, 2, and 3. So there's 3 independent bivectors here, which I've labeled as planes. So we have 1 scalar, we've got 3 vectors, we've got 3 bivectors, and then we have 1 trivector, which represents the volume. And so this is also called the pseudoscalar. The highest dimensional object in any geometric algebra is known as a pseudoscalar. Okay, so the beauty of this is that the rotations work identically. I can rotate in this E12 plane using the exact same formula as I did in 2 dimensions. And so that's really the power and the motivation behind moving to this, because we're going to start talking about the Riemann Sphere, which demands that we do rotations in 3 dimensions. So that's why we needed to introduce this. Okay, but geometric algebra is obviously takes more than just a few minutes. So if you want to learn more, please check out this book, Geometric Algebra for Physicists by Chris Duran and Anthony Lacenby. It's a very good book. There's also a couple other books, one by Leo Dorst and another one by David Hessen, which is very good. Okay, now on to the Riemann Sphere. Okay, so the Smith chart, it represents all passive loads within a closed space, which is the unit circle. Okay, this is a big mathematical advantage to doing computations, because it gets rid of a lot of singularities with impedance and admittance representations. Okay, so similarly, the Riemann sphere is going to represent all loads, not just passive ones within a closed space, the unit sphere. So what we're going to have to do is take our plane here, which I'm going to label the S plane, or reflection coefficient plane. It's called S because it's going to be like S parameters. And we're going to map this plane onto the surface of this ball onto a point P. Okay, so E1 and E2 are the 2 vectors that describe the plane of the Smith chart, the S plane. And then E3 is just a dimension we've added. And that's a standard thing, stereographic projection, of how to map this point onto a plane, onto this point on the sphere P. Okay, so the reason we're going to do this is because all load representations, so S, Z, Y, are interrelated through rotation. So this is much simpler than the normal bilinear formulas. So let's look at this graphical example here. So here's a slice of the E13 plane. So if we back up and look at this, here's E1 and E3. So E13 is a plane that's described by these 2 vectors. So it's kind of this slice. Okay, so if we look at that slice and we imagine that we're just looking at a reflection coefficient S in that plane, then we're going to stereographically project it on the sphere P. And then to do a transformation to an impedance space, we're going to rotate it along this plane by a given angle to P sub Z. So now we have the impedance representation. So if you down project back to the plane, you'll have the impedance value. Similarly, you can go from impedance to admittance, and then you get a value over here. This is a complex inversion between these two values, obviously. And then this rotation is actually occurring outside of this plane. So anyway, once you do that, since rotations form a group in 3 dimensions, you can find the Py to S pretty simply just by composing the S to Z and Z to Y. The other advantage is that the inverse of the transform is just rotation in the opposite direction. So you don't have to invert a Möbius transformation, you just have to put a minus sign in an exponential. That's a huge advantage. Okay, so here's the basic idea. We have quantities that are existing in the plane, reflection coefficient and impedance, and they're related by a bilinear transform. So we don't want to do that because it's complicated, so what we're going to do is up project onto a sphere, and then we're going to implement that same transformation through rotation and then down projection. So this is really similar, this diagram, to a Fourier transform, except we're using projection to linearize Möbius transformations. Okay, so in the paper, this all worked out in details, and we find that there's the specific rotations which change the different basis sets, and so we define them like this. So R sub ZS is, by definition, a rotor, which is just a rotation, which transforms a vector from S to Z. And this is, just so you know, it's explicitly given in the paper by something like this, which is a pi/2 rotation in the E13 plane. Okay, so as I said earlier, rotations are implemented with the sandwich formula. So to actually find the point PZ, we form this. And this tilde over here means reversion. So that's, you'll have to learn more about geometric algebra to figure that out. But it's not complicated. It just changes the sign of the exponential for a rotor. And so I've defined another rotor here to be the reversion of R sub ZS is R sub SZ. The reason we do that is so then when you have a rotor sandwich formula, it's obvious to tell which domain you're going to because the subscripts on the inside match and the subscripts on the outside are where you're going to. So that is our motivation for labeling it like that. In either case, it's a simple rotation in 3 dimensions that can be expressed like this. Okay, so let's have an application of this. So we're going to use the group property of rotations to find the input admittance expression for a matched transmission line. Input impedance expression, sorry. So we know that a matched transmission line and reflection coefficient is just a simple rotation along the Smith chart. So it's like a SWR circle. So it's going to be e to the rotation in the E12 plane. So we know that, and we know how to translate between impedance and reflection coefficient. We know how to up and down project from the sphere. So we can figure out the rotation and impedance domain. So you can imagine that we're going to take impedance, we're going to go onto the sphere, we're going to move to S, P sub S representation, then we're going to apply this, which we know, then we're going to go down, and then finally down to the plane again, and then what we're going to get is that the L sub Z operator is equal to the sum of the composite of these 3 sub-operations. Okay, so just to recap, we're going to take the original vector Z, up project it to the sphere, yielding P sub Z. And this up arrow just denotes up projection. And then we're going to transform to the S parameters using this formula. Finally, we're going to apply a matched transmission line operator like so, and then transform back to the impedance space. Okay, so these are all the different steps, but we can write it all in one line because it's all just rotation, so it's simple. Okay, so just to describe what this one-liner is, so here's our P sub Z point, then here's our Z to S transformation, then here's our line transformation, and then back to Z. Okay, so once you do this, you can kind of say, okay, well, this thing on the left, I could group all this together and call this a single operator. This thing on the right is just the reversion of this thing on the left, so it follows the rotation form. as expected. And so here we've now found the operator for a transmission line in the impedance domain. So, and you note that this is the same thing as taking a load and rotating it from one basis to another. So we say that the operators transform identically to the loads. This is really important for algorithms because it's really simple and clean. So this is known as covariance. The other advantage is that you'll see that if you look at the paper that the operators have the exact same form in both bases, Z and S. So we say that the CGA is domain invariant. Sorry, the Riemann Sphere is domain invariant. Because there's no reason to apply the matched line in one domain or the other because the form are functionally the same, which makes sense. Okay, so what are the problems? Why don't we just keep using the sphere? The problem is that adding admittance and impedance, which are essentially translations in the impedance or admittance space, they're not easy to do on the sphere. You can do them, but they're not linearized easily. Okay, so what's the solution? We're going to add another dimension of negative signature, which means the vector squares to a negative number. Okay, so the geometry gets more sophisticated, but the idea is the same. That's important. So we're essentially doing the same thing, except instead of going to the sphere here, we're going to move up to some four-dimensional space. Okay, so now we're going to talk about this conformal geometric algebra. So the idea is we're going to extend our stereographic projection model by an additional dimension with negative signature. Like I said, that means squares to the -1. And then we're going to model the reflection coefficient as a vector in this four-dimensional Minkowski space. Okay, it's also interesting to note that this geometry is that of space-time, so it's well understood, and rotations in this space are known as Lorentz transformations. So here we're going from the sphere to this four-dimensional space. This is just a 3D projection of that because we can't draw four-dimensional spaces. Okay, so we have an orthonormal vector basis. E1, 2, and 3 are vectors that we've already defined. And then we're going to add to it E4, which squares to a -1. It's expressed like this. This basis generates the geometric algebra of these elements here. We've got one scalar, 4 vectors, 6 bivectors, 4 trivectors, and 1 pseudoscalar, which is a quad vector. Okay, in the E12 plane, that's the original space, so you can think of that like the Smith chart if you want to. And then the E34 plane, this consists of the added dimensions, and that's sometimes called the Minkowski plane. Okay, so we'll go through, in the paper we go through how to do translations in this space, and this is well documented and known. So we just express the results with respect to circuit theory here. So when we add admittance and impedance, if we look at the effects in the reflection coefficient domain, we'll see that we get rotations that are defined by these planes. So in 4 dimensions, you can get basically non-simple, what they call bivectors, which are sums of independent planes. So it's a more complicated space. Okay, but the nice thing is that we can use results of group theory using a thing called a commutator product, and we can find a bivector group starting from these 4 bivectors, and then we'll see that it consists of 2 new vectors, bivectors, which are the E14 and the E23 planes. And these so what we can do is, okay, take all these bivectors, we can generate rotations in all of these, and then project it on the Smith chart and see what it looks like, and use our intuition to see what we got. And here you'll see that, as expected, the rotations in the susceptance and conductance sweep out curves as such. And similarly, the resistance and the reactance do this. These are familiar curves of Smith chart. And then if we look at the paths by the N and Q bivectors, which we found using group theory, we can recognize that these are actually impedance scalings, so characteristic impedance scaling, and then this is a phase shift on the impedance. So these 2 things combined are actually known as a Carter chart. We prove this in the paper. It's trivial to prove, actually. Okay, so the nice thing is that rotations in 4-dimensional space are Lorentz transformations, like I said. And so now all the theorems about Lorentz transformations, like their decompositions and things like that, can be interpreted in circuit theory, and vice versa. So all equivalent circuits can be interpreted as given decompositions of Lorentz transformations. So it's really a unifying idea, which is nice. Okay, let's move on to a semi-practical example of this model we've generated, on to analyzing the distributed circuit model. So this is generally how transmission lines are developed in circuit theory. So the transmission line model is essentially infinite repetitions of a given unit cell, and the unit cell consists of infinitesimal discrete elements of reactance, resistance, susceptance, and conductance, and it's usually expressed in a diagram like this. Okay, so now that we know how to implement the addition of each one of these elements, we can just add them all up. So this is just a series of rotations in each one of these planes that we've defined earlier by some normalized amounts, which are given by these lowercase variables here. So this is a total rotation for this element, this unit cell. Now, if these unit cells are taken down to infinitesimal amounts, so we take the limit as their values, their parameter values go to 0, then we'll find that you can just sum up all of the bivector planes. So normally you can't do this with a non-commutative algebra, but in this event you can. Okay, so this unit cell is just a rotation in this bivector, which is some complicated bivector, which looks like this. Okay, so here we can see it's a rotation in 4 planes, and the amount of rotation in each one of these planes is given by these expressions relating their reactance and susceptance and conductance and resistance. Okay, so what do we do with this? Okay, well, we can see what's actually going to happen here. So if we consider a lossless case, so we're going to ignore any resistance or conductance terms. So these two planes will disappear, and we'll get rotations in just these 2 planes, E12 and E24. Okay, so if the values of susceptance and reactance are equal, then we'll get just normal Euclidean circle rotations, SWR circles. Okay, that's a matched transmission line. If the values of the normalized susceptance and reactance are equal. Okay, but if we make something a little bit more susceptive, then we start to get a mismatched transmission line, and so we notice that the match point starts moving a little bit to the left here. And if we take this in the extreme, where basically there's no reactance, then you just get rotations in B, in susceptance, which is what we saw above, and this is a similar thing with the other in the other direction, so more reactive. So you can really use this to study mismatched transmission lines in a very concrete way, and we can generate these things. These things are kind of hard to describe mathematically. You have to cascade, a matrix of an impedance step and a matched transmission line and things like that. But here we can express it all as just one rotation. Okay, so the advantages are that our model, we can describe the distributed element transmission lines without differential equations. Okay, we did take a derivative, if you remember, of a rotation, but that was it. So that's kind of interesting because it's a totally different approach to a problem. Whether or not it's better or worse is not really that important. It's just the fact that it's completely different is what's important. So the geometric interpretation of Z0 is different also. So we can imagine that here's our Z0 of our mismatched transmission line, the characteristic impedance, and we interpret that as the axis of rotation. So we're in a 4-dimensional space, and this is a 2-dimensional projection of that, but that's the interpretation because it's invariant to the rotation, which is what the characteristic impedance is. Okay, so now systematic equivalent circuits can be systematically explored because we're describing everything with a bivector algebra, and we can systematically compute all different possibilities of rotations and decomposition. So that's a huge advantage. Okay, finally let's conclude. All right, so what happened? So what we did is that we now have a way to represent a change in basis from reflection coefficient, admittance, and impedance with rotations in 4 dimensions. So we've taken this fractional linear transformation or Möbius transformation here, and we've converted it to a rotation. Okay. We've also shown that adding admittance, impedance, and transmission lines and transformers are also rotations, and they form a group. So we've taken formulas like this, which is the input impedance of a transmission line, and we've converted it to a simple rotation. Okay, we've also shown that there's a bivector group with discrete elements, and that you can use this bivector group using an operator framework. Okay, this is very useful for algorithm design. Okay, we've also made steps towards unifying analysis tools with physicists. Okay, we've already mentioned that with terms of Lorentz Transformations and other things, and that's really helpful also. Okay, so how do we verify everything we did here? So there's a couple software packages we use. There's one numerical Clifford Python module called Clifford, which you can get at this link. These are all open source, obviously. There's also a symbolic module which we used for a lot of the computation called Algebra, and that's you can find at this location. So all of our results have been verified to be equivalent numerically with their complex counterparts. Okay, so what's the future? So the future is that we're going to make a thorough analysis of the operator. So since we've replaced cascading circuit elements with rotations, we can do a lot of analysis on these and replace basically a lot of matrix representation of two ports and things like that. This is also very amenable to periodic network analysis like filters and things like that, because rotations can be interpolated and each interpolation step can be considered a unit cell. So we've already done some work on that. Like I said, also we can use this to develop equivalent circuit models and figure out when to stop, basically based on group theory. Finally, we need to work out the foundations of our theory from space-time algebra. So instead of using essentially complex results and just translating them, we need to generate the results from first principle. Now this is not going to change our results because the complex results are not in question. We're just arguing that they're inefficient. But to have a holistic model with geometric algebra, we need to do this. And finally, we like to apply these tools to other areas of wave mechanics, such as quantum potentials and things like that. Any wave dynamic system, we should be able to apply these tools. So that's what we're looking to do. And the end is not showing up, but this last slide here, let me move in. Oh, shoot. Okay, well, anyway, this is the end of the presentation, and I appreciate your time, and I hope you enjoy the paper.